This is a quick demonstration of the Axis Cranks pill physically. It's about 36 millimeters diameter, 14 millimeters thick. This is the ANT transceiver on one side. The other side we've got the electronics. You can't see any components there on the underside of the board. The top side of the board is where the battery is housed. The batteries are CR2032 3-volt battery. What I'll do now is demonstrate the forces we can get out of this crank by squeezing the thing. Sorry, I said crank, I meant pill. This is a simple interface we've developed for testing the pill. It doesn't report power, it just reports force, and it reports the force 4 times a second. That's more due to the bandwidth of ANT than anything else, but what I'll do is I'll put the battery in the pill. And you will see up in the corner there, these numbers have popped up. It lets us know that it's actually talking to the pill via, I don't know if you can see that there, that's just an ANT dongle, USB dongle. We'll read our calibration factors out of the pill. There they are here. And we can correct for our offsets in the pill here. It basically just does an automatic 0 using the DAX in the microcontroller to offset the instrumentation amplifiers on board the pill. Have a look at our graph output. You can see we've got almost 0, minus 1 Newton for our tangential forces. They're in red, and I'll average about minus 2 or something for the radials. A little noisier than the other ones. Now, the pill also has angle sensors in it for measuring the rotation. And I'll just turn the angle on, turn these two off, clear that, and see if we can demonstrate angle change. Difficult to do really, but there we go. I'm going through one full revolution and now another full revolution. Okay, go back to our forces. Here they are. Now, the orientation you're looking at the pill now is the way it would be in a crank that was pointing up. So we'll call it 12 o'clock. It's also, if I get the angle right here, you'll see our angle changing at the top of the page is 180 degrees. If I squeeze top and bottom, watch what happens to our graph. Now that's a radial force, which is a compression force in the crank. When you put your weight at the top, dead center, straight down. You're not pushing forward, you're just pushing down the crank. There's the force. If I squeeze across this way, that's the equivalent of standing on the crank when it's at the bottom of stroke, and you can see it goes fully negative. Do that again. Okay. Now, it's a pretty standard setup with the web inside this pill for measuring these forces, but the measurement of the torque or the tangential loads is a bit more difficult. We're using a shear method to do that, which means it's a bit difficult to show shear in this pill just by squeezing it. We'll get some signal, but not a lot. If I go 45 degrees here and squeeze this, I've introduced some offset into that as well. I'll turn this radial off so it doesn't upset us. There we are, that's what's actually really happening. So here we are squeezing this, negative, 45 degrees that way, 45 degrees the other way should get positive, and that represents the sort of forces you'd see when you're looking at tangential loads in the crank, which is actually the torque producing moment that we calculate power from. So that's a value of, this is actually calibrated, but it would measure newtons or newton meters, depending on what we wanted. So if I turn both channels on again, you can see we've got forces going all over the shop there. I'll clear it so we get better scaling. Give us a squeeze there. There. Here's the red one coming up. There it is again. Again, I'll turn off the radial forces, which are the compression and tensile loads in the crank that are used for measuring effectiveness of your pedaling technique. Turn those off. This is now solely looking at what would be the tangential loads in the crank. The same sort of forces that you'd measure with SRM or power tap or quark or whatever. That's it. That's the Axis pill in action, ready to be installed in a bike crank. Thank you.